We're discussing rejection sampling, and we started out talking about the uniform case. We were thinking about how to sample from the Mandelbrot set, and that was a fun little problem to think about. And we found that we could do that using this rejection sampling technique, where we drew uniformly from a bigger set, and then we threw out the samples that didn't fall in the set we were interested in. And now we're taking a look at the non-uniform case. And we're going to focus on the case when we have a PDF, a density that we're trying to sample from. But this works for discrete random variables also. So we're given here, the setup is that we're given this f tilde, this function f tilde, which is proportional to the PDF we want to sample from. F is the thing we want to sample from, and it's some super complicated thing. And one thing that I should have mentioned here is that mathematically speaking, if we know f tilde, then we know f, because in order to get f, we just need to integrate f tilde over the whole space, over Rd, and that gives us alpha, the constant of proportionality. So mathematically speaking, f tilde gives us f. But computationally, there can be a big difference. Computationally, f tilde may be very easy to evaluate, and f may be very difficult. So actually carrying out that integral to get alpha can be extraordinarily difficult. So the assumption here is that f tilde is easy to evaluate or compute. And f is not necessarily easy. Okay, so what is the rejection sampling algorithm? I'm going to give an algorithmic description of it here, and then we'll prove the more sort of formal statement for why it works in a minute. In another video. So here's the algorithm. First, we need to choose what's called a proposal distribution. Proposal distribution, and let's call it Q. Q is going to be some PDF, so this will be a PDF. And Q needs to satisfy the property that there exists some constant C where c q of x is greater or equal to f tilde of x for all x in Rd. For all x in this d-dimensional space. So we need to be able to scale it up so that it's greater or equal everywhere. And so that's a hard constraint that we need to satisfy. And a soft constraint is that, and I'll go into this a little more detail, there's a couple of soft constraints that we will want for Q to be a good proposal distribution. I'll mention one right now. One is that we need Q to be easy to sample from. We're going to sample from Q, and then we're going to get proposals from Q, and then we're going to reject some of them according to a random criterion. So that's the first step, choose Q. The second step is we draw a sample from the distribution Q. So we sample x from Q, and then, given x, we sample y from the uniform distribution on the interval from 0 to cq of x. Actually, that should be capital X, capital X. And this is the conditional distribution, so we're sampling from the conditional distribution given x here. And the third step, step 1, step 2, and step 3, the third step is the rejection step, possible rejection step. If y is lesser, well, it'll be rejecting depending on what happens with y here. So if y is less or equal to f tilde of capital X, then we take some new random variable z to be equal to x, and otherwise we reject, we quote unquote reject this sample that we got from 2 and return to step 2. So if we reject, we go back to 2 and we try again. We start anew, we get a new sample from Q, and then we get a new sample from Y, given the new sample of X from Q, and then we check to see if we satisfy this constraint. We keep going, we keep looping here until this is satisfied, and then we stop, we quit, and we get our sample. And our sample is this Z, this resulting Z. And so the result is that the output is Z. So the output is Z, and Z is distributed according to our target distribution F. This Z here. And in the next video, we'll prove why this is correct. Why, in fact, this algorithm gives you a Z which is distributed according to F. So first, before we do that, let's think about the intuition of what's happening here. Let's draw a new picture. So let's draw a nice big picture here. So the proposal distribution is Q. Actually, first let's draw F and F tilde. F, let's say F is, let's make it some sort of make it something like this. Maybe F goes something like this. Something like that. And F tilde is what we know, and maybe that's bigger. So it's proportional to F. If I can draw that. Oh yeah, okay, close enough. So maybe this is like, I don't know, 3.24 times, 5.6 times F. So this is F tilde. This is F tilde. And this was F. Now, what do we need? We need a Q. We need a Q that is, and F doesn't have to be greater than 0 everywhere. I'm sort of drawing it that way, but maybe it's like 0 over here or something. Well, maybe it's 0 out here somewhere or something. But it doesn't have to be strictly positive. Q we need to be such that there exists some constant C such that CQ is greater or equal to F tilde. And Q needs to be normalizable, so it's some distribution, and let's say, I don't know, maybe we do like a Gaussian or something like that. Maybe it's something sort of like this. Maybe that's Q. That's Q. And then let's draw CQ. So CQ we'll do in this nice green, rich green color. CQ, we scale up Q so that it's greater or equal to F tilde. It's testing my drawing skills here. Actually, we might not hit that one exactly. Let's say we're a little bit greater there. Needs to be greater than F tilde everywhere. So maybe it's something like this. Okay, so this is this Q scaled up. This is CQ. And that was Q. Okay, so it touches here. That would be, maybe that's the best C that we can get, the smallest C we can get. It touches here and it doesn't touch anywhere else, maybe something like that. Okay, so we've drawn the picture, and now let's think about what the algorithm is doing. So we had our f. What we get is actually f tilde, this yellow, maybe crazy sort of thing. We chose q, and then we figured out what cq needed to be. And now we're ready for this step 2. So what's going on here? We sample from q. So maybe we get a sample maybe like here. We draw a sample from q. So let's say that's our x. And then we draw a sample from the uniform distribution from on the interval from 0 to cqx. Well, the interval from 0 to cqx, we can visualize it vertically as this vertical sort of thing. This was cqx right here. So it's this vertical, it's this interval. If we sort of turn it on its side, turn it vertically. We draw a uniform sample from this, and maybe we get something here. So maybe that's our y. If that's our y, then we go to step 3, and step 3 says, is y less or equal to f tilde of x? F tilde of x is here. That's the point on the yellow line. And it's not less or equal. Y is not less or equal to f tilde of x. It's greater. And so we don't accept, we reject. So we would reject that y and return to step 2. Okay, so we reject that y. We return to step 2. And so we reject that. Well, we don't reject x, but we reject that whole iteration. Okay, so now we draw a new x. We return to step 2, we draw a new x, and our new x, maybe it's, I don't know, something like, maybe it's here. X. And we draw y, we have this. Again, we draw y uniformly from this, and maybe this time we get this point here. That's our y. And now y is less or equal to f tilde of x. F tilde of x is right there. Y is less or equal, so we accept, and our sample is this x. So z is our sample, and it's this point right here. So z is this point. And in general, if we had rejected that one, I mean, we wouldn't have rejected that one, but if we got a point up here when we drew y, then we would have rejected it, and we would have had to draw a new x, and we would just keep on doing that over and over again until we got a y that landed underneath here. So that's the algorithm for rejection sampling. And I hope the intuition is clear. The basic idea is that we're drawing these samples from this proposal distribution. We're drawing these proposals, and then we have a random criterion for rejecting. And that criterion is going to be, it's more likely to accept when the true distribution is large, and it's less likely to accept when the true distribution, sort of represented through f tilde, when that is small. So like if we had a point out here, if x landed out here, then this would be very small and we'd be almost certain to reject, right? On the other hand, if we had a point here, if this was our x, by some miracle it landed right here, then we would be certain to accept. Almost, I mean, maybe not quite at the point, but if it happened to be right there, then it would be certain to accept. Or if it was this one, then we would just almost completely certain that whatever y we drew was going to land under this yellow curve on this interval. Okay, so that's the intuition. That's the algorithm for rejection sampling in the non-uniform case for a PDF. And next, we'll take a look at the formal sort of statement of why this is a valid procedure. Why it gives you true samples from the target distribution F.